Welcome to section 2.7, derivatives and rates of change. So we have spoken in previous sections about the concept of a tangent line to a curve. This is a line that crosses a curve at exactly one point. And in this case, we're saying that the tangent line to the curve f of x is crossing at this point, a comma f of a. We'll label it the point P. This is a line through P with a slope of m, which can be found by taking the limit as x approaches a of f of x minus f of a over x minus a. This is just a reiteration of the slope formula, the average rate of change formula. And by letting x approach a, we are getting closer and closer, infinitely close, to the tangent line. So basically, what's happening here, we have our value a, the point P. We draw this secant line between our point P and some arbitrary point Q. This produces a slope. This slope of the secant is an average slope. It is an approximation to the slope of the tangent line, which is, of course, this line here that touches the graph only at that single point P. What we're doing by taking the limit as x approaches a is saying, okay, instead of x being all the way over here, what if x was right here, a little bit closer? Now we draw that tangent line, that secant line. Notice this line is closer to the tangent one we're looking for. Move x a little bit closer. Draw another secant line. Move x even closer. Draw another secant line. And you can see if we were to extend these, they're getting very, very close to the tangent line in question. The idea is if we keep going and we keep getting closer and closer and closer to the point P, all of these average rates of change, these slopes of the secant lines, will become the slope of the tangent line. So we can use this formula now with our knowledge of limits to actually find the slope of a tangent line, even though we would technically need 2 points to find slope traditionally. We don't need that restriction anymore now that we have limits at our disposal. So let's take a look at an example. Find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. So our slope is going to be the limit as x approaches 1 of f of x minus f of 1 over x minus 1. So we get the limit as x approaches 1. F of x is just x squared. So that's x squared minus 1 over x minus 1. This is a case where direct substitution isn't going to help us just yet. We need to manipulate this algebraically. So we take the limit. Notice this numerator is factorable, so we get x plus 1 times x minus 1 over x minus 1. We get that cancellation, which gives us the limit as x approaches 1 of x plus 1, which of course 1 plus 1 is 2. That is the slope of the tangent line, but be very careful when you're reading these questions. This problem is asking for the equation of the tangent line. So the equation we can find using point slope or slope intercept form. So we start off y minus 1 equals 2 times x minus 1. So distribute that 2. We get y minus 1 equals 2x minus 2. Add the 1 over. We get y equals 2x minus 1. And that would be the equation of this tangent line. found by taking the limit of those average slopes, those slopes of the secants, until it gave us the slope of the tangent. Now, we have an alternative version of this formula that we are going to see much more often used in calculus. So it's the same problem, but it's kind of being relabeled and framed in a slightly different way. So consider the distance between x and a being called h. So instead of x minus a, we're replacing all of the x minus a's with h's. So here we have, right, our point P, we have the point Q, which is h units away. So this distance here is h units. So as x approaches a, h approaches 0. Because if x is getting closer and closer to a, the distance between them, that's what h is getting closer and closer to 0. This formula then becomes the slope equals the limit as h approaches 0. So again, instead of x approaching a, we have h approaching 0 of f of a plus h minus f of a all over h. And this version of the formula is the one that you will typically see used in calculus and beyond. They are equivalent formulas, but the standard typically is to use this version. So let's try an example with this one. Find an equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. So to find that slope of the tangent line first, we get the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. It's very important to maintain the limit notation consistently throughout the entire problem until you have actually taken the limit. So the limit needs to be there the entire time. So let's substitute in 3 plus h into the function. So it's going to go in for the x here. So this is going to be 3 over 3 plus h minus f of 3. So that's 3 over 3 all over h. And yes, these problems can tend to get a little bit big. So this limit as h approaches 0, 3 over 3 plus h minus 1 all over h. Now, with this setup, just like we saw in previous cases, we cannot use direct substitution here because h becoming 0 would be a problem in this fraction. So we need to do some manipulation. We need to play around with the algebra a little bit first before we can do any substitutions. So what we're going to do, we have this fraction up here and this minus 1. Let's try to combine these into one single term. So I'm going to give them a common denominator of 3 plus h. So this is going to be limit as h approaches 0 of 3 over 3 plus h minus 3 plus h over 3 plus h all over h. Be very mindful of distributing this negative to both of those terms. So we get 3 minus h over 3 plus h. Oops. And you know what we can do? Instead of keeping this all over h in this complex fraction here, dividing something by h is the same thing as multiplying it by 1 over h. Like that, right? Division is just multiplication by the reciprocal. So we can go ahead and just multiply this by 1 over h, and that's exactly the same thing. So up here, we have 3 minus 3. We have negative h. And down here, we have 3 plus h times h. H up here, h down here. Let's go ahead and cancel those out. So we have the limit as h approaches 0 of negative 1 over 3 plus h. Now, direct substitution is a valid solution method because now we are in this domain where h is not producing an undefined or unreal value. So we get negative 1 over 3 plus 0, so negative 1/3. And of course, we would like to celebrate because we have done a lot of work to get to this number. But again, be mindful of what the problem is asking. It's not asking for the slope of the tangent, it's asking for the equation of the tangent. It would be a real shame to get to the so close to the end of the problem and end up not actually answering the question. So the equation, if we substitute that back in, put it in slope-intercept form, we would get y equals negative 1/3 x plus 2. That is the equation of the tangent line. As we've seen in previous sections, we can describe things such as velocity in modeling problems using slopes. In particular, we can use the slope of the tangent to describe instantaneous velocity, so velocity at a specific moment in time, not over a time interval. So velocity in terms of time can be written as the limit as h approaches 0 of f of t plus h minus f of t all over h. So again, the same formula, but now just put into a different context. So a ball is dropped from 450 meters above the ground. What is the velocity of the ball after 5 seconds? So remember, the position function is given by 4.9 t squared. And what we had to do before was take the intervals, from 5 seconds to 6 seconds, from 5 seconds to 5.1 seconds, and get approximations for the velocity after 5 seconds. Now that we have limits, we can find the velocity at that instant using our limit as h approaches 0. So f of t plus h, let's go ahead and just put what that is here. So this is our formula, so that's 4.9 t plus h squared minus 4.9 t squared all over h. And as we will see with so many of these types of problems, the simplification and algebraic manipulation is key. So we'll go ahead and distribute this out. We'll FOIL this out. We can even factor the 4.9 out all the way if we want to. So we'll get the 4.9 out here. FOIL this out, so that's going to be t squared plus 2th plus h squared, and then we still have this minus t squared left over all over h. We have a t squared minus a t squared. And if you look at what's left, notice there is a common factor of h in both of those as well. So we can actually go ahead and factor that out. So we have 4.9h, and what's left is 2t plus h all over h. And just as we needed, those h's cancel. That removes that undefined restriction. So we just have limit as h approaches 0 of 4.9 times 2t plus h. So that is 4.9 times 2t plus 0. So 4.9 times 2, that's 9.8 t. Now this isn't the answer. Remember, this is just the formula for the velocity. We want the velocity after 5 seconds specifically. So after 5 seconds, v of 5 is 49 meters per second. And that is the instantaneous velocity. That is the velocity at that specific moment in time after 5 seconds have passed, not an approximation, not an average over some interval. Now, this process that we've been doing here for the last few examples, this idea of an instantaneous change, or the slope of the tangent, right, that we've been looking at here. This comes up so frequently in calculus. It's a huge major focus of study for us, so it gets its own name. This is called the derivative of a function f at a number a. The notation we use for this, it looks like an apostrophe, but it's read as f prime of a. So this is f prime of a is our kind of standard notation for the derivative. So f prime of a is precisely this limit as h approaches 0 of f of a plus h minus f of a all over h, assuming this limit exists. The derivative represents exactly what I was just talking about. This is the slope of the tangent line to a curve at a specific point, or alternatively, the instantaneous rate of change of the function at a specific point. So no longer are we looking at slope of the secant or an average rate of change. We're looking at slope of the tangent or an instantaneous rate of change. So if we look at this last example here, find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. So just at some arbitrary constant value a. So f prime of a is the limit as h approaches 0 of, so we have f of a plus h. So a plus h has to go in for all of these x's here. So I'm going to make some bigger brackets here. So that's a plus h squared minus 8 times a plus h plus 9 minus f of a. So that's a squared minus 8a plus 9 all over h. This is going to give us a long string of terms that will hopefully simplify nicely if we want to have a chance of solving this problem. So let's go ahead and go through these. So we're going to have, FOIL this out, a squared plus 2ah plus h squared minus 8a minus 8h plus 9. Distribute this negative, minus a squared plus 8a minus 9 all over h. And now if we look at what we have here, notice we have an a squared and a negative a squared. We have a negative 8a and a positive 8a. And we have a 9 and a negative 9. So those are all gone. We are left with 2ah plus h squared minus 8h all over h. And there is a common factor of h in each of those. So we pull that out. We're left with 2a plus h minus 8. These h's cancel. And now we can apply the direct substitution. So the h becomes a 0, and we're just left with 2a minus 8. So this result would be the derivative of this function at the number a. Or in other words, this represents the slope of the tangent line at the number a, or the instantaneous rate of change of the function at the value of a. If we had picked a specific value for a, like 3, we would find f prime of 3, we would just plug in 3. So that would be 6 minus 8, negative 2. If we wanted the derivative at 5, we would plug in 5. So we get 2 times 5, 10 minus 8 is 2, et cetera, et cetera. This is how we develop formulas for the derivative, which we will be looking at in section 2.8. But that completes section 2.7.